progress starts. And the same, of course, you speak about Boltzmann. Of course, it was not his particular contribution, but he introduced concepts of an atom, which of course invisible and same, you cannot anything, you have at that time at least, even now you don't have direct access to them, you introduce atoms and you have a new world of understanding of the world, you introduce something which is unknown. And this unknown, you develop a language how to talk about that, but Boltzmann done how to manipulate an atom, introduce entropy, etc. Right? And the same about Mendel. He introduced genes. And he didn't say these words, but we have, some features being inherited, and just to want to understand them. It was not purely theoretical, but he made lots of experiments. And by the way, he was mathematically educated, and for that reason, his work would not be accepted. Yeah, because by all this time, he didn't know multiplication table, not a job. Darwin specifically, we know by his papers, he couldn't compute, he couldn't add numbers. Yeah. He couldn't tell, he had intuition, but he never could make computation with numbers, make mistakes. When he was computing, he had one of his points that he was very point. And I come to that. He was evaluating how many elephants will be left 500 years after from 2 elephants, and he gives data how many they produce. By the way, it was a little bit wrong at that, but that's material. And then he gets a number in millions of thousands. So he said that there will be 20 millions, but if you make computation, it will always 80,000. And he cannot make computation. He just, he divines. Yeah. He doesn't know how to compute. And that, he was one of the smartest people of the time. And with Mendel, this was remarkable communication with somebody called Nageli. And Nageli was a great scientist of the time who more or less shaped modern botanics. He described the plants, how they grow, all this microscopic analysis, and do it perfectly well. He couldn't understand a word of Mendel, and he just completely dismissed and giving him meteoric advices. And Mendel was kind of a shy man, he was not a professional scientist. So he accepted it. That's quite remarkable. And of course, indeed, biologists, for this day, they don't understand Mendel, and they like very much Darwin, because they say Darwin explained evolution, which is fantastic nonsense. He doesn't explain anything. Right? He suggested, and that's very important, correct language in which term he can describe evolution. He emphasized it. He didn't invent it. He emphasized it. All arguments he gave were wrong. Everything Darwin was saying factually was either repetition of other people saying or wrong. However, he gave the right perspective. And that's kind of must be understood. Everything almost, with a few exceptions. Yeah. There were people arguing with him. Yeah. Darwin had more authority. He was very kind of eloquent. He convinced people. But then everything was wrong. And there is history of that, which is completely distorted for a variety of reasons. One of them is quite amusing. People assign something to Lamarck and say, Lamarck said that and that and that. And then you ask people, well, you take the text. It was English translation. It was wrong translation from French. They just, words illegally distorted. And another thing interesting about this, he was kind of advisor of Cuvier. As many happens, students hate the advisors. And Cuvier, when Lamarck died, the laws kind of very sarcastic text about him. And this considered as a kind of document when citing Lamarck. So that's about biology and evolution. But what remarkable thing about evolution from our point of view, that despite the fact that Darwin didn't understand mathematics, literally couldn't compute, he has a real understanding of that. And he realized that the essence, the language describing evolution is in mathematics, nothing to do with biology. Any idiot can understand that. And the point is, we have exponential function, right? The only way you can put it into final space, we cut off. And this cutoff of exponential function called selection. And this, of course, was known to people, but Darwin realized, probably Wallace at the same time, that this is a major means to describe evolution. It's a language. It explains nothing. It tells you nothing. And Darwin actually understood this. But the people following him, not quite understood. They were not. They knew, like Fisher, for example, was mathematically really understood mathematics, but he amazingly didn't understand these points. And for example, he was misinterpreting Mendel, whom he respected very much. His history fantastic, because this history reminiscent of what may happen with the understanding of the mind. And the major block at that time with Darwin done was, of course, not this mathematics. It was resistance to the common opinion about evolution. And it was already prepared, because 20 or 30 years before Darwin, there was a book by some journalist, actually, describing more or less what Darwin said. It was a common knowledge. It was not so scientific as Darwin was. It was called the Vestiges of Creation. I've forgotten the name of the author. He wrote this book and was read by everybody, including Elizabeth, the queen of the time. Everybody knew that, and then Darwin wrote kind of, in a way, kind of elaboration on this text, certainly. And if you look at the poetry of the time of the nature read in close and close. There is a kind of poem by somebody, Tennyson, I think, yeah? Written 20 years before Darwin, where several lines exactly describe what is called, this fittest survive. All this kind of nonsense, all this rhetorics was already there, but Darwin gave it some setting, and of course, there is idea of this exponential function attributed to Malthus, which is, the way you know, this what Malthus speak about population, people speak about Malthus. But now what Malthus wrote, he never invented that. It was Condorcet who discussed it about more or less at the same time, 30 years ago, prior to that. But Condorcet describes it and explains what you should do with this. He says more or less what we now down say, particularly kind of politically correct people, what you should do. And Malthus said, no, it will not work. That and that isn't, because you can't beat exponential. No matter what you do, whatever measures you make, exponential will kill you eventually. And this is what Malthus was saying. And he didn't invent that. He was not that smart. But Condorcet, that's what he is, a very smart guy. And he had a very interesting story about it. So history of science tells you something. But what to do from there? Okay. Now, we have to understand, so what happens in the mind? And I'm saying, well, my point is that there is some unknown, which we don't know what it is, and unless we can emphasize, try to understand it, we never understand what mind is and what is the relation between brain and the mind. And so just, because it's a mathematician, let's look at the following formula and see if you can, just before preparation, Penrose wrote a couple of books about artificial intelligence and about the mind, on the Emperor's New Mind, and he made the following point. The distinction between any artificial intelligence and human mind is that human can understand the Gödel theorem. And if you don't understand the Gödel theorem, then you're a robot. And a robot can be cheated also because you can't robot. And again, it's exactly mathematical statement. No experiment was done for people checking how a population understands Gödel theorem. If you don't understand Gödel theorem properly, as to the robot, you are a robot. No, but I give you another kind of thing. When you don't understand that, you must be a robot. So I have to give the answer of this. And if not, yeah, but if I knew that. I cannot believe you will do it. So givetvis så annorlunda. Good. So, my way of giving an example. So what is this sequence? So you see, just this is one of the points I want to make. From all my respect for it. Yeah. But by the way, about Freud, we come to Freud. All my respect for Freud. Yes. I think that you cannot make psychology, this is not a joke, if you don't understand that. It's not completely. Not exactly maybe this formula, and this was kind of done by very. You know who wrote this formula? It's Ramanujan. One of his first formulas is Ramanujan. And the question is, we have to understand, if you try to understand psychology, how he made this formula. So you have to make a model, mathematical model, which will reduce this formula out of the input he has, or compare it. And that's. But now I want to give you something more elementary. What is it? What is the sequence? And that's explained by the very difficulty which you face everywhere in science. I think it's a good example. Yeah, it goes for the die. I wrote it up to this number. Remember. Of course you cannot guess. But this is how this we observe. This typical thing you may observe in biology. Or in study one, you see something, and they're numbered like that. There's no way to guess it. Or I would rather say there is no logical way we know approach it. You can guess if you stare for this for a long time, you can see. These are numbers, are integers of cubes. Differences of cubes, yeah. So 7 is 8 minus 1. So 19, whatever it is, I don't know. don't remember. I wrote it down. And that's not the quantum numbers in the atoms. The Bohr, the rule found by Bohr was exactly like that. There were differences of numbers, like that. The frequencies you observe in the spectrum of that, and from there quantum mechanics starts, realizing a certain sequence was the station. Right? And this way, and therefore, unfortunately, there is no rule. You have to be a Bohr or somebody looking at the data and make it ideal. There is no kind of primitive. It's not you observe something, you make a conclusion. It's completely wrong. It never works in a non-trivial situation. But it may happen that there is something simple then projected by some man. And this is how our mind functions. Input it has. And from this projection, I have to go out. And there is no rule. At least we don't know the rule. However, something is possible. So, now, what I wanted to say, I make this note. Now, what about Spalding? Yeah. What was about this guy? So, what's so great about him? And if you want to understand the mind, what does it mean to understand? Right? And this is a kind of tricky point. So for that you need, also from my point of view, whenever you have such a word and you're kind of scientist or mathematician, you have to imagine a mathematical model for that, not just referring to something. And the answer by no means may be easy. Right? Maybe before going to Spalding, look at another example. Okay, maybe say Spalding, then I'll bring another example. So, and you want to, and one point I want to make, maybe I just say it, understanding meaning in general, maybe universal model. So your way presenting it should not depend on what you're going to explain. If you already from the very beginning, in your theory, you put in concepts which you want to explain, it's cheating. And this is usually how psychology works. But you have to do something which is not there. And that was done by Spalding in the case of psychology. Right? It was the first step, understanding psychology in terms which were not kind of very simple, but not immediate there. Right? And this is called imprinting. He discovered imprinting. And he made some experiments. And imprinting is when the young animal, for example, how a chicken recognizes who their mother is, who is your mother, how they recognize that. They don't have a program in their mind describing how a chicken or how duck looks like. They have a universal rule, and that's these rules which determine their mind whether a chicken or a human, this we assume, and this is the first moving object. So his discovery was the first moving object taken from other, and now usually referred to Lawrence, who was not the second to discuss it, but he received the Nobel Prize, but he was a smart guy. He understood animals very well. But and Spalding is a very sad story. He was a poor man, and at that time only rich men could make science, like Darwin. And this is Darwin essentially so famous because he was so rich, not because he was so great. Because, say, Wallace was a better scientist, of course, than Darwin. He was a poor man, and Darwin actually bought him off. He gave him position, and so they wouldn't compete for the discovery of the evolution. It's kind of tricky thing. Though Darwin certainly was not a bad man by the time, despite all that. And he actually had clearer, in many respects, clearer picture, conceptual picture. Though everything he was saying was wrong, in particular, the main principle of Darwin was continuity. He believed there is continuity. And you know where this idea of continuity comes from. Yeah? Now I keep forgetting the name of the guy who kind of started this idea. And it was some of the disciples of Pythagoras. And how he proved the idea of continuity. I don't know if Pythagoras actually subscribed to this idea, but this man done. What was his name? I didn't make his name. Because he wanted to become strong. He was considered the strongest man in ancient Greece. Yeah? And what he was doing, he put him on his shoulders a calf and walking this calf around. The calf was growing and growing and growing. Getting stronger and stronger. He became a bull and still was carrying it. And this was the idea what Darwin was kind of trying to put into the not a joke. That's the idea of continuity, very much propagated by Leibniz. And this happens to be completely wrong. You know, evolution is this continuous process, which was saying people around Darwin all the time, like Cuvier. It's not continuous. Continuous evolution leads to nowhere. Just it leads you to death, more or less, to the elimination of species. If there is continuous evolution, you're dead. I mean, population die, not immediately, but all changes in evolution which we observe were discrete. And that was point made by Mendel, but with Mendel was another very amusing point, because what Mendel has shown, and then it was big problem with biologists, and this is the following thing, it's a mathematical point. What Darwin was saying was kind of obvious kind of mathematics. You only had to go against certain trends, and trends were very funny. For example, people were sticking, maybe not, maybe even at the time of Darwin yet, that there is life may come from slime, from nothingness, self-generation. What was the main reason why people believe in that? What was the argument which was accepted? Because they knew at that time that there were about 1,000 species of different parasites living on Earth intestine. And if they were all created simultaneously, they couldn't believe in Adam, Eve, and their intestine couldn't contain so much parasites at the same time, and it would be strange kind of Adam, right? If they in the paradise they were leaving all these parasites in their intestine. Therefore, these parasites must have come later, after creation. It was not a joke; it was really ugly. And Darwin was kind of not accepting this kind of argument. And this was a major point of Darwin. There was a moment when you can say openly that nothing special about people, nothing special about creation, evolution, but everything he was said before him by Buffon, for example. Buffon was, as you know, a mathematician. He knew all that, but he was saying all that, but saying, no, but I don't believe it, because the scriptures written this and this, so it must be this. No, it's logical to say this, but I don't believe it. And he had to listen because some of his books were burned, but he was not saying this. And Darwin said it. So that was okay. So it was not so much of his scientific, but kind of conceptual and kind of proper. But now this what you have universality. Imprinting is universal phenomenon. It's not independent specifics. And these universals determines possibly your mind. And this universal you have to understand. And they're not something which come kind of immediately to one mind, though it's very simple. This is an instance, it's something you see. But in general, it may be something you don't see. And on the contrary, Freud, who came 50 years after Spalding, was doing opposite. He was explaining psychology in terms of cultural concepts, like history of Oedipus, Oedipus complex or something else. Yeah? And that was doomed to failure for that very reason. Because if it was so simple, it was done already when you were yet on the trees. Yeah? When everything you come as a human cannot have such a trivial explanation, like Freud was suggesting. And he has so again, he made some impact similar to that was done by ideological part of Darwin, and then this kind of, we can make interesting observation that what's common, say, to Darwin, to Freud, and to Marx, or their followers, and you wouldn't find, for example, for followers of Maxwell, because this there are Marxists, Darwinists, Freudists, there is no Maxwellist. Nobody cares, so it's just two. It's ideology. It's interesting, yeah. So they have lots in common. And different people, you listen to what they say, the way they express, they speak of the same emotional kind of tonality. Right? And therefore, we will be very skeptical, even if they're, of course, it's Freudian, and cannot be right. But Darwinists sometimes Marxists say something correct. He will get trust, he will know whether it's correct or not. And because they're driven by something else. Now, so what we know, from where we can extract information about our thoughts. Maybe meanwhile I'll write some of the formula. Go to indication. What it will be. hard to get. It's one with pi. It's also a monovision from that. And this is, by the way, one of the best formulas for computing pi. It's very fast conversions. Quite remarkable formula. And again, if you don't understand, assume you're wrong. So mathematics tells you something. Yeah, something remarkable happens in the brain, and you cannot ignore it. So again, one point I want to make: no study of the brain of mind. I don't know how brain works. It's not our business, but how the mind works, it must be at least tangentially explained that. Because you see, when psychologists speak about numbers and how they're being perceived, they usually look at the people, but the amount of experiment they make the same they make with pigeons. Now, pigeons can count, make pigeons, and then say, we shouldn't, okay, well, that's mathematical, ingrained in us. But it's not mathematics as we know. And what makes us human is different mathematics. And mathematics is a tricky point, but what we have in common, and which is more visible for everybody, and which is for that reason much harder to understand, is working with the brain in the language. Right? So, another point I want to make, it is a comparison between language and mathematics. Why? Mathematics is more amenable to understanding for rational analysis compared to the language. They have something in common, in the second word, they have in common very simple formalistic way. But the problem with a language, because almost everybody has this ability. And mathematics is more rare. And for that reason, it's better to study. And phenomena which is common, it's very hard to analyze because there is no sufficient diversity. Because usually you see differences, you don't see absolutes. And mathematics, there is more diversity between kind of how people, those who do mathematics, how they learn. And for that reason, mathematics is much more instruction. At one point. Another point is that language is being learned by children at the time when they're psychologically, they're very different from adults. Right? You know, if you look at even neurologically, if you compare the neural network of somebody of 6 years old and 9 years old, it's completely different pictures. Right? The way synapses being distributed already at that time changed dramatically. So up to age of 9, roughly, children have very different way of thinking. They have a different brain. And therefore you assume they think differently. And we know children think differently. The perception of reality is not for adults. And that's when they learn language. And so we never can understand how we do that. Mathematics you don't usually relate. And therefore you may have some recollection. You can make some experiments with people how to learn, trace this learning. There is a chance of doing it. Right? And it's one point. Another point, and this has come related to the language and related to other point I want to make, how you study languages or how you study mathematics. So these are rare phenomena, right? Writing such formulas are rare phenomena. And so, in the language, there are kind of two lines of thought. And how to understand language. So one thing we should accept, and this was emphasized in recent time by Chomsky, and I don't know history enough to say if he would be first or not, but language is very much projects the way you think, and not so much semantic of the language, but the syntactic structure of the language. That is reflection of the structure within your brain. However, it's a very tricky point because, again, say Chomsky was emphasizing and saying that there is universal grammar, and so all languages are very much similar and have certain general rules, and there were great discussion what these general principles are. However, it was said in the 60s, when he wrote his main article, the became most influential linguistics. And by the way, himself, he was a student of Zelig Harris, who was first mathematical linguist, who mathematically analyzed English language. But then what was happening, people were studying languages. There are on the earth now between something 6 so many languages, and they die kind of one language a day. So what you say today will be only tomorrow. They keep dying very fast. And some majority of, let's say 90% of languages maybe spoken by fraction of a percent of all people. There are big language covers almost everybody, and then there are tiny little groups of people speaking about them. And now they're being studied, and the point is, whichever general principle you find in linguistics, you always can find a language, you will count the example. And this was not known until recently, because the study kind of was developing quickly. And unfortunately, many languages are dying before you know, and small languages especially like that. And one language about which I read is Firaka people, quite interesting with that. Because when you think how a language related to human mentality, this was quite interesting story. So it's about probably now only 200 people who remain there, and they have a particular language. The language has 3 levels. You can speak, you can sing, or you can whistle. There's 3 different modes of communication in different situations. Apparently in this language there is no concept of color, there is no words for colors, and there is no concept of number. It's unclear if there is concept of two. Right? And apparently only 2 people truly understand this language. It was very interesting. Sorry, there were 2 American missionaries, the family of their name, husband and wife, who lived with these people. And they were kind of Christians, and they were teaching them. But at some moment, the man became converted against Christianity because he was saying that these people have much better philosophy, much more humanistic, and they themselves rejected Christianity on the following simple basis. They speak about Christ, and they say, oh yeah, it's very great, very interesting way he lives, he dead. He's no use, because we care about who knows who are alive. They have very interesting, very kind of good, small community, extremely kind of humanistic. They have no idea of keeping things. Yeah? Everything they have immediately shared, because nothing can be kept. They have no idea of property or anything. But now, of course, it's changed. It was maybe 20 years ago. Now the language is kind of absorbed. All of Portuguese. They live in Brazil, in Amazonia, and this certainly changing. And this system, and then he divorced his wife. His wife didn't convert to this philosophy, and he divorced. And then he was speaking to linguists, and linguists were coming and saying, "Oh, you are not right. They do have concepts of color. They bring them together, and they show them some object with the same color, and no, they say the same word." And he said, "Now bring another group independently. They use different words." So they were comparing to a different object, and they were together. They were deciding how this like blood, or this like flower, and they were saying that. And if you don't understand the language in detail, you become completely confused. And secondly, the language has recursion, at least according to this person. So the main point, which I very much emphasized with Chomsky, and up to somewhat absurd point, in my view, that the point of a language is recursion. You can say the same thing, iterate many times. The dog, that shade, the cat, that killed the rat, that, ta. And the point, you systematically said, the major property of languages, infinite repetition of this thing. But infinite, and that's an interesting point. In order to understand languages, you have to understand what are numbers, and what is infinity, and what is probability. And this, maybe, I want to say some words about that. So, languages do contain, a significant part of our thoughts. Exactly the structure, the formal structure of the language. And it's different for different people. So we suggest that it's not it's a universal structure, but it's not linguistic structure. But what as mathematicians, what we want to think, there is mathematical structure, which goes beyond languages. And some of the structure we know, and this one of these numbers, right, and probabilities. So this I want to discuss in application to this issue. So what is numbers? And what is probability? The point with numbers is that nobody properly understands what numbers are, for the following reasons. That mathematician has mathematical kind of experience with numbers, but not too good a thing when it comes to real numbers. Real meaning that you meet in the world. And as a test, let me give you the following. So what is bigger? The number of hairs you have on your head, not like me with you, and people in the Olympic Stadium. How we can compare this number? What is the orders, which is bigger, which is smaller? What can you say? That's more or less the same, and there's 100,000. And this on the hair you can actually, if you think a little bit, you can actually even compute it. Right? But the way what I read, I don't know whether it's true or not. But there is a great correlation, now it's related to what you're saying, between people who don't understand numbers and those who believe in the flying saucers. So these people cannot have the difference to say how many people live in San Francisco. 10,000, 100,000 to 10 billion. They just can't believe them to say. On random. And they believe in flying saucers. It's about half and half population. People tend, of course, to believe in flying saucers, who don't understand large numbers. And so, and these numbers, big numbers, we ought to understand in order to understand what happens with our minds. And but of course, the limits, what are truly big numbers, is kind of not quite clear. But in a second, maybe I say 2 words about that. And then about probability. So the biggest number which I know, which comes kind of in the real world, is related to Schrödinger cat. Yeah, I probably write something wrong, but it's something like 2 to the 2 to the 2 to the 2 something. I think it's power like that. Secretly sitting, describing Schrödinger cat. And this, by the way, exactly why this discussion is so absurd. It's a statement about this kind of numbers which have no realistic meaning. The question is, if in certain conditions, whatever was experiment, the cat may be dead, the cat may be alive. And certainly some state can be considered as dead and some being alive. The number of this opinion, I think, was this order of magnitude. Because how many states a cat has? So it consists of about 10, if I'm not saying 26 atoms of molecules. Right? So the number of states will be, say, each of them will be in 10 different states, will be like that. And then there is opinion whether it's true or wrong. So the number of opinion about if this cat, this is why people discuss about it for so long. And these numbers, of course, are completely meaningless, and all discussions are completely meaningless for that reason. Another, say, discussion which appears in Penrose is not so dramatic about this finite automaton, there is a robot, finite automaton, But this finite automaton, like a computer, I think today a computer would have at least 10, how many? 10 to 10 digit states. And you have this easily 10 billion byte memory, so even more than that. We can even have to share that. Huge number. Would mean finite automaton. It's not. It's fine because you have finite automaton. You have a picture of a graph, you say that. So making this is a huge number, and therefore any discussion when you just think, oh, it says finite automaton, and apply kind of basic theorem of that, kind of completely absurd. And this is actually interesting story because it started with Boltzmann, when Boltzmann was describing kind of the system and whatever, and Cermel, I think, brought up Poincaré theorem and saying there is recurrency. It's measure preserving set, therefore there is recurrency, and so you recur, and so you cannot have, say, second law. The physical system, statistical, must come back to where it started. But this has comparable number of states, so it may come back. Whatever this word means, may. But it's certainly not possible in the universe we have. This which was not understood by Cermella. But another interesting point, again, about Boltzmann is very instructive. Still, it was accepted, and assumed what he was saying was not rigorous. But the point was, it was not rigorous because mathematics was not ready to express what he was saying. He was saying in the language he learned from school, it was the language of 19th century mathematics, and today, my tendency to say what he was saying was expressible only on the language which appeared in the second half of the 20th century. And this was non-standard analysis, and he was definitely all the time speaking in this language. And secondly, it was functorial kind of mathematics, because his equations are not truly equations. They are functors between certain categories. And then everything becomes absolutely rigorous. There is no question of the convergence of statistics. Everything can become perfect if you translate it to the right language. So the issue is, what is the right language for that particular purpose, or the language, say, for axiomatic of the mind, which we don't know. Probability is there. And this is another quite amusing story. That probability, as we know it, formalism, was the present formalism due to Kolmogorov. But if you look carefully what he was doing, he was just repeating what Buffon was doing. He just was making, in set theoretic terms, describing what done by Buffon, who was, by the way, not a predictory mathematician. He was kind of scientist with general type. Namely, the idea is quite simple, that you always can think as probability as area somewhere, and your event just subsets which area is defined. And that is kind of geometric probability. And he proved some general things. And this was done 70 years ago, or in Toches, yeah, 8 years ago. And it's still being accepted. And this, of course, cannot be said. No reasonable theory can exist more than 50, 60 years later. And example, so if you look at the logic of this probability, it's very much similar, which was almost at the same time, being 40-something. It was algebraic geometry, how it was formalized by André. André found this very similar. Here, this universal probability space by which you describe whatever happening in the world probabilistically. And André had these universal fields where you can take points of all algebraic curves. But then, with André, soon thereafter, Grothendieck came up, and now it just nonsense. Nobody was followed away. You know, it just was wrong. Right? He was using exactly a concept he was prepared for him beforehand, set theory. And then Grothendieck used new set of concepts, category theoretic language, and you know that's how today we speak about algebraic method. Of course, hopefully in 10 years it will be used. And probability still stick to that. And this annoys very much scientists like Chomsky, who of course don't understand this problem. They say, oh, probability is not applicable to languages. Because this kind of probability is wrong probability. And so but if you start thinking in slightly relaxed terms, say about languages, you immediately have different schemes, understanding what is the first steps, understanding what is a language, and how you may try to describe, working of the mind underlying this language. And probability is one of the simple things. What is probability of a sentence? So I try to make, by the way, some, Chomsky, by the way, partly motivated by that, made his famous sentence. It's colors, green, ideas, sleep, furious. It's a famous sentence. He was designing as a random sentence. Always highly non-random, yeah, because there is this negative kind of correlation between like colors and green, and they're kind of in the same basket, these two words. Or sleeping and furiously, they're also in the same basket. And actually, I tried myself to make random sentences, but it's extremely difficult. So I actually take the list of words and put exactly having the same scheme as Chomsky, and putting first will like that. And so what one of them, and just if you look here, it doesn't so meaningless. Illegal migrant department complain half-heartedly. Yeah? And this makes sense. It's very difficult to even on random to make a meaningless sentence. Yeah? So what is probability? What is a random sentence? Yeah, it's very yeah. And you can start borrowing from internet, and then again, an interesting example which was happening when one of the first corpus of the language was collected, about 60 million words. I believe that one of the most common words, the third and the second common word was thou. Am I spelling it correct? Thou. It was one of the most common words. Because, of course, the Bible was one of the major texts they used. And that's a common word there. And so and then immediately the question comes, what is probability of a word? Not speaking about sentence. So Chomsky was saying, no, there is no meaning of probability of a sentence, no matter what you do. And he's completely right. Not this kind of probability. It's not a number. So probability for this purpose, and a general kind of conjectural theory of probability, which I think will branch into many different parts, probability is not a number. Probability is a functor from one category to another, from a complicated structural category to something more amorphous like numbers but not numbers. And here it's quite clear what it is. Because if you look at a real text and you take string, I think 50 letters, such sequence uniquely determines everything where it's contained. So if you know such string, you can say exactly which book at which place it is only once. It's predominant probability, because we have 20 letters, and so we have 20 to 50. It's a huge number, much more than the number of texts existing on Earth, ever spoken, will be spoken by human beings. Therefore, such a string determines all books, sentences, whatever. So we have to forget about the rest of the thing. This is the only reality, these strings. And now you have actual word, some string, and then contained in longer strings. And they go branching. And so probability of this sentence is not a number, but this string. So you don't know what language is, but you know what probability is, which is not the final word, I must say. This is just indication where you can look. So you have to change concept of probability. You have to change concepts of number, and change, adapt mathematical kind of concepts to the reality of languages, and hopefully it will bring you next to your mind. And coming to your mind, though, I'm finishing. So what are kind of mathematical things involved? And I just finish by one. So this is one of the points. So this is kind of probability. Of course, this is on the beginning, but I want to make one little mathematical trick which is used systematically in languages nowadays, but not systematically, but used in bioinformatics, solving the following equation, which we do so. Yeah. And it is as follows. Say in languages, you want to know which sentences are possible. And imagine we have here a table of pairs of words, which we have in our mind. And this may be easily, in our memory, we have about 10 to the 6. And here there are 10 to the 6. This, and some of them may be coming together. So this is a million, but 10 to the 12 is a trillion, which is a big number. And certainly we can't remember, our brain is okay, but we don't remember so much. Right? Because input which goes to us, you know how many seconds you have in your life. You know, by the way? How many seconds? Hmm? So in a billion seconds, so 10 to the 9, it's about 30 years. So it depends how long you live, but so you cannot learn too much. Yes. So trillion is completely out of it. Of course, you don't learn just 1 word per second. And that's one of the points was made by Chomsky. He kind of emphasized that. There is a poverty of stimuli. So you learn so little, and so little goes to the child learning the language. And then, however, pretty fast, by day 4 or 5, children just start speaking. How the hell possible? Because they have to fill in this kind of entries. Right? Because they know how to combine that. They may learn million is a small number, millions 2 weeks. Yeah. Million seconds, just 2 weeks. It's an incomparable numbers, yeah. This one thing about understanding numbers. Million, billion, there's nothing in common in your life. Million is real, billion not. So you have experience. And so you can feel it also by something of order of a million. If you do it in a couple of years, you may have here 10 to the 7 entries. And the question is, can you on the basis of that know any value here, at least with a reasonable degree of precision? And here there's a major mechanism which is present, we know, in biology and in languages, and at least in evidence why it's a good way, how you want to solve this question, and simultaneously classify these entities. And the point is there is classification. Namely, you have reduction to this matrix to a small one, like 1,000 by 1,000. Namely, there is a map of the space of column and the space of rows to smaller sets. They from million go to 1,000, and the matrix from trillion goes to million. And this 10 to the 7 go here, but now they fuse pretty well, you know. They become very representative. And then you say, any entry here must be just pulled back of entry. And
so what is this? What is this?
And there is a map. If such a map exists, right? You can prove again with a overwhelming probability it will be unique. Probability you make an error if you found such a map, and it fits, yeah. Probability of making a mistake is just virtually zero. Constructing it as it is a NP problem, you cannot solve it just easily. But in practical situation, there are algorithms how to do that, because matrix is not structured. But once you have it, you solve this problem. If such map doesn't exist, then you cannot learn. So the point is, you cannot learn anything unless there are these reductions. And reduction, and this is, I think, is a basic ingredient of learning. Yeah, this kind of math. And of course, it's present this neural networks. It's always hidden in this matrix. If you lose this math, everything is there. And one interesting instance of that, let me finish it. Linguists didn't like this when it first appeared in linguistics. And because when you apply it, they classifying words. Of course, you can make prescribe the size of this matrix, there are many exceptions. In particular, in this way, you can classify different words and see how do you classify it. And then it was done, and when easy with a small matrix, easy to make. And they found that the particles, these were separate, and this was together with this. So one of these was particle, article, and this was a pronoun. And linguists were annoyed and said nonsense, it was wrong. But then, it was about 30 or 40 years ago. But then they looked, some of them, in history of the words, and they realized that these words have nothing in common. They just artificially brought to the same group, and these are indeed in the same group, for very good reason. And now it is accepted. However, this is kind of a very simple example saying, and the point, yes, I want to make, the only way you can study language, you have to forget fully the meaning of that, because this meaning fools you all the time. Yes, you think you understand the meaning of words, whatever. You are fooled by yourself all the time. The only way to go very far away, to make something very abstract skill, and try to understand how it may work in principle mathematically, and then superimpose it and to make experiments. Right? And this is essentially how it works in physics. It is a mathematical scheme, but it must be checked when you apply it, see if it responds to the reality. But you cannot be here even more than physics, guided by your intuition. So your intuition, your culture, everything you know, is just exactly what prevents you from learning. And we know this was example, this was manifested in history of biology and evolution. And I think the same is here. But here the difficulty is twofold. First, you have to block your knowledge, and secondly, you have to invent mathematics, which was not the case in biology. Mendel actually invented but very simple mathematics for his purpose. And yeah, I didn't say what was his kind of theorem, and the point was, let me say, I concluded, this is a kind of great mathematical theorem discovered by Mendel, very simple, and then they discovered by all kind of proven rigorously, by Hardy and Weinberg. And this is, if you look at the Google and see how much Hardy is being cited, and how many his papers cited, let's say approximately, we find so much for Hardy, or Hardy Littlewood, or whatever, all his theorems. But if you look Hardy-Weinberg principle, it will be, I think, about like that. But by far more significant contribution to science he made, and what was the theorem? And the theorem was called, he hardly proven a very special case. I think it's a Mendel had in general, you have a matrix. And this is completely counterintuitive. In second CMI it's all counterintuitive. And you do the following thing, you add column, add row, and put here the product of the two. So from the face of matrices on the n, you manage to insert this quadratic method. And this corresponds how being features of animal gene being redistributed after random matching. Right? And so in practical, quasi-practical term, you have flowers here and flowers here. This is blue, these are red. So there are lots of blue, a little red. There is a mountain separating them. You remove the mountains, and mix it up, and you have a new distribution. And then people say that fittest survive, so this are better. Darwin say, repeat it, and then eventually this will become extinct, and this will dominate. However, as Mendel realized, nothing will happen on the second step. If you keep being like that, and that's why evolutionists were very much annoyed. There is no evolution in this level. So in this Darwinian naive scheme, there is no evolution because of this mathematical theorem. And what mathematical theorem says, when you have this map from matrix to matrix, it's important. Square of this equal to this map. And this is a quadratic map, which is absurd, yeah? The degree must grow. However, something has lots very simple, of course. And Hardy wrote some formulas without understanding what happens in the language of matrices. Yeah? Just wrote a specific formula for 2 by 2 matrices, symmetric matrices. Let's check this formula, Mendel. And this was one of the objections to Mendel for when it was rediscovered in the turn of the century, 30 years after his discovery. And you know why he was discovered, why people actually started citing Mendel, because other people, I forgot his name, who discovered it, and they were, of course, fighting for who was the first. And then some of them were, it was already Mendel. This is the only reason we know about Mendel. We wouldn't heard of him otherwise. And he was understanding it probably even better because he understood mathematics also. They learned more biological. So, and this again is very simple mathematics. And this is not at all highly counterintuitive, right? Something happens on the first step and then stops. And this is very different from mathematics used by Darwin. And this is what discovery, that's the fundamental difference. Mendel made discovery, both experimentally and kind of mathematically, that there are discrete units of inheritance, whatever they are. And they're not the abstract entities. At the time he discovered them, they had no physical manifestation. And still, it was clearly understood by people like Morgan, whatever, you didn't need their physical manifestation. You could do a lot. And from there, science, as we know, it developed, not from Darwin. Darwin can throw him away, nothing could change. So purely kind of that stuff. And for that reason, in this country, there's great controversy with Darwin and non-Darwin. It's absolutely irrelevant, that discussion. The science is somewhere else, and it's much more profound, and most people don't know it or don't give a shit. Everybody understands Darwin, because there's nothing to understand. Philosophy. And however, it's remarkable philosophy. It still shapes your mind and I think extremely instructive, but not very non-scientific. Great, probably the last great philosopher, Darwin was the last great philosopher, was really great philosopher. Was saying, and what interesting thing, a lot of nonsense ascribed to Darwin he never said. Trivial sentences, he was not non-trivial guy. He was obsessed with the idea of continuity, that was a major mistake with me, and lots of technical mistakes with me. However, he was right at one point, and one of his points was, he was saying that any time you face unclear situation, the only guide which is for you is mathematics. He was saying, you have to do it mathematically, and forgetting, so to speak, your kind of reality, and then you may succeed. And this is how to proceed. And this, I guess, you have to do it also here. But mathematics, so you have a chance to do something.
Neuroscience, you often make advances through experiments. Do these considerations suggest any experiments you'd like neuroscientists to do?
Yeah, it's certainly very difficult to make experiments. Let me give another interesting example. Yes, this I don't know experiment. I give an example of some psychological experiments which may be kind of fundamental and really know to do. And this, because I was just speaking about religions, there are various theories of history of religion, origin of religion. In my view, they're all nonsensical. People just say what they already know. They say, well, we want to explain that. This is one great theory, due to Julian James, which describes emergence of religions at certain period of, at least in the Mediterranean, at the period of urbanization. When urbanization started, religion appeared as ecological phenomenon. And he describes conditions under which they appear. And this condition can reproduce. So you have to take children, beat them hard, make them work hard, and put in them some kind of, forcing them to do something, and then they invent religion. Okay, and this, he said, this is what happened when urbanization came. People didn't want to make experiments, they were really forced to do that. And in their mind, religion emerged, and this description is called bicameral mind, something by this guy. It's very interesting. I recommend greatly the book. He died with Julian James, he was in Princeton as philosopher. And this very kind of, it may be wrong, but it's an example of scientific theory, but it's verifiable, and it's explain phenomena which you observe by something you don't know. And this is a good example. And the same, of course, what I'm saying, of course, I don't know experiments. I must admit, the way I can see experiments in silica, I think you can make some problems, and you have to again in a proper way, which will imitate the way you think. But then you have to exactly to do that. You have to remove from the practice which you do. And some of that has been done by people in robotics. So I know one group in France who made robots based on these principles, and they're quite amusing. So their robots not taught anything; they're given only universal general principles, and they first behave, like that, and then in the course they evolve much faster. Then people, in the course of several hours, you start behaving extremely similar to how babies at the age of 3, 4 months behave. They react to sounds, they turn to each other, produce sounds similar to which they hear, etc. And then, unfortunately, it doesn't go, the last I spoke to these people, that didn't progress. And maybe they now do it better, but there is a fundamental difficulty. So my understanding is that in all approaches, there is a fundamental problem, fundamental difficulty, and you face it on many levels, but it's always the same, kind of, it has the same flavor, and we have to understand what it is. And we don't understand. One of the languages which I spoke to people who work on machine learning and languages, and I was suggesting this universal algorithm, this kind of evaluating how they would work. And then what you find, if you follow this kind of logic I described, you observe that the most difficult part of the language is not what you think it has some subtlety or metaphoric, whatever. That's easily can be handled by very formal algorithms. But very difficult to understand correlation between nouns and pronouns. And there is, and then I spoke to people what they do, and they, apparently, if they do with all data on the language, they have the same success, which means 0, meaning 50%, which means 0. Because it is obvious examples we know, and then slightly more complicated, you don't know what. You don't know what pronouns are. They're very logically complicated entities. We have no mathematical explanation of pronouns are, and we cannot for that reason to extract them from the language automatically. Of course, the problem should be which knows nothing about language. It must have universal principle, extract certain correlation, and then will be called noun and pronouns, and we have to have formal indicators saying they correspond to what happened in the language. And then you accept such model. You see, any model which will already put in there what you know, it's not trustable. You can explain anything if you do that. And that, like, you know, say in mathematical physics, so we have Hilbert space, operators, the top with this data, you get results, and then you make verification. You start checking afterwards. Okay? You don't, at every moment, you said adjust parameters at every step, of course you can model everything. And that's the problem with languages, because it's very difficult to forget what we already know. But besides, we don't know what are the right things. So we know what the wrong things is, and we use it. We don't know what the right. But experiments is difficult, because phenomena, psychological phenomena, which appear here, they're usually long-term. They are not fast. So experiments done by psychologists usually very fast, and also very much biased. Let me give another example. But I know some experiments were done by these children, and they say the best way to predict how successful a child will be is to make the following test. You offer him a candy and say either you eat it now or tomorrow, but then you have to order. And those who can postpone, they will be more successful. But I'm not certain it applies to mathematicians, or to artists in general. Yeah? To some category of people who may be successful, but not in a certain particular way. And exceptional phenomena, like people like Ramanujan, may be more informative for the following reason. They are, of course, anomalous. But this anomalous may be more instructive because you can see something. Because, you know, the true experiment is not imitating what happens in reality. You create artificial situations. And this is a point which was kind of made by Claude Bernard, who was also one of the greatest scientific philosophers of the time of Darwin, comparable to him. The opposite to what philosophers usually say. You don't observe reality as it is. You make it artificial, only then you can understand it. Or you have artificial observations. The artificial phenomena you see in nature, the most remarkable ones which you know are supernovas. And these supernovas happens once in 200-300 years. None was observed after the invention of telescope. And they tell you more about the nature of stars than everything else. And this actually was one of the key points in the time of Galileo, that it's not a supernova. I think some nova appeared, and they changed perspective that heaven is unchangeable, according to Aristotle, philosophical. And then it was a basis for making the model of function of the star by Fred Hoyle. It was exactly observation of supernova, that way they behave, and and he predicted, made fantastic prediction of our new nuclear reactions, theoretically, looking at them. So exceptional phenomena, in a way, more informative than statistically common. But it's very also difficult hard to formulate. Therefore, we have this data. We have somebody like Ramanujan. We have to understand this, incorporate this in statistical kind of more common people. But experiments are very difficult to make. And you observe sometimes people and see how people react to this or that, and you see how much there are barriers which we don't want to know what happens in other mind. They say, well, I have a kind of personal kind of anecdotal evidence, but very convincing, very much. Well, everybody knows mathematics probably experienced that. You give a lecture, and then you talk to somebody, and somebody doesn't understand what you say. Everybody experienced. And then a year later, this guy writes a paper exactly saying more or less what you said. And he doesn't know where it came to his mind. He forgot this completely. That was brooding for him for years and then coming back. Yeah, I had experience many times. You listen to lectures and nothing. And then someone, oh, I know that. And then my other speakers go, of course I told you that, yeah. 2 years ago. Well, I accept it. I cannot remember this, but I accept it. I know it happens because you observe the other side. So, this is an interesting phenomenon. There's a barrier preventing us to see the way our brain works, and I think there is a good reason for that. Because people, when they become open like Ramanujan, they're not survival types. They don't give children, this is not inheritable. It's a pathology. Disease. Being a genius is a disease. So it's very hard to make an experiment. But in silica, you may try to do that. And they have to invent it. I thought about that, but I don't have good experiments.
Any other questions? Okay, so...
We have a question.
Yeah, I was wondering, the use of mathematics in physics has been tremendously successful in the University of Mathematics.
Right.
I was wondering if you can have the same hope for biology to have a deep mathematical understanding of
It's
biology.
new. It's mathematics, but different from what it was so far. We didn't know which mathematics. Mathematics is a huge kind of thing. Yeah? What means mathematics? It's another we haven't discussed. What is mathematics? The only good answer we don't know. And you are so stupid. Right? You don't know when you say mathematics, which mathematics? You don't know what it's. Oh, excuse me.
Okay, anyway, so Mikhail Gromov will be here for today, so you get more questions.
Hello?